Mastering algorithm efficiency for large datasets in today's data-driven world, the ability to process vast amounts of information efficiently determines the success of software systems. Whether building scalable applications or optimizing machine learning models, understanding algorithm efficiency becomes essential for developers working with large datasets. This guide explores fundamental concepts and advanced techniques for evaluating and improving algorithmic performance. We'll examine how different approaches impact resource consumption and system responsiveness while providing practical strategies for achieving optimal results. The importance of algorithm efficiency. Efficient algorithms form the backbone of modern computing infrastructure. As datasets grow exponentially, inefficient solutions become unsustainable due to increased processing times and higher computational costs. Consider a social media platform handling billions of user interactions daily. A poorly optimized recommendation engine could cause significant latency issues, affecting user experience and business outcomes. Time complexity measures how execution time increases with input size. Space complexity evaluates memory usage relative to input size. Scalability determines if an algorithm remains effective as dataset sizes increase. These metrics help developers make informed decisions about implementation choices, balancing accuracy with performance requirements. By prioritizing efficiency early in design phases, teams avoid costly rework later stages of development cycles. This proactive approach saves both time and resources over project life cycles. Evaluating time complexity. Big O notation provides a standardized way to describe algorithm performance characteristics. It focuses on worst-case scenarios rather than average cases, offering predictable bounds for analysis. Common complexity classes range from constant time, O(1), to exponential growth, O(2) to the power of n. Understanding these categories helps identify potential bottlenecks before implementation. For instance, searching through an unsorted array requires linear time, O(n), whereas binary search achieves logarithmic time, O log n, on sorted arrays. Selecting the right data structures often leads to significant improvements. Hash tables enable near-constant lookup times compared to linear searches in standard arrays. Space complexity considerations. Memory constraints play a critical role in algorithm selection, especially for embedded systems or mobile applications. Efficient memory management prevents out-of-memory errors and improves cache utilization. Recursive algorithms typically consume more memory due to function call overhead. Iterative implementations often offer better space efficiency for similar tasks. Data compression techniques can reduce storage requirements without sacrificing functionality. However, decompression processes may add additional computation time. Balancing trade-offs between time and space complexity depends on application-specific requirements and available hardware capabilities. Practical implications of inefficiency. Real-world applications demonstrate the tangible consequences of poor algorithm design. Financial institutions relying on high-frequency trading algorithms require millisecond-level precision. A delay of even 10 milliseconds in order execution can result in substantial financial losses during volatile market conditions. Optimized algorithms prevent such risks effectively. Web services handling millions of requests per second must minimize response times to maintain service quality. Inefficient back-end logic causes cascading failures across distributed systems. Database indexing strategies exemplify how proper optimization transforms query performance. Without indexes, simple lookups degenerate into full table scans. Optimization strategies. Caching frequently accessed data reduces redundant computations and database queries. Implementing smart caching mechanisms significantly enhances overall system throughput. Divide and conquer approaches break complex problems into smaller components. Merge sort and quicksort leverage this principle for efficient sorting operations. Dynamic programming optimizes overlapping subproblems by storing intermediate results. Fibonacci sequence calculations benefit immensely from this technique. Pipelining allows parallel processing of task segments, maximizing CPU utilization across multi-core architectures. Advanced Techniques Amortization Analysis provides deeper insight into average case behavior. This method helps understand patterns in seemingly expensive operations. Probabilistic algorithms introduce randomness to achieve faster results with acceptable error margins. Bloom filters illustrate this concept well in membership testing scenarios. Deterministic versus non-deterministic approaches present different guarantees about correctness and runtime characteristics. Choosing appropriately depends on problem domain specifics. Approximation algorithms find near-optimal solutions quickly when exact answers aren't feasible. Traveling salesman problems utilize these methods extensively. Performance testing methodologies benchmarking tools measure concrete performance metrics against defined criteria. These tests reveal actual runtime behaviors rather than theoretical predictions. Profiling identifies hotspots consuming disproportionate resources. Memory profilers detect leaks while CPU profilers highlight intensive operations. Loading test environments replicate production-scale scenarios accurately. Stress testing pushes systems beyond normal operating limits to uncover weaknesses. Load testing simulates concurrent users accessing systems simultaneously. This reveals scalability limitations and potential failure points. Best practices for developers' code reviews should prioritize algorithmic efficiency alongside functional correctness. Peer feedback catches subtle optimizations missed during initial development. Refactoring legacy codebases introduces modern efficiencies gradually. Incremental updates maintain stability while improving performance characteristics. Documentation explains rationale behind chosen algorithms, helping future maintainers understand trade-off considerations. Continuous integration pipelines automate performance regression detection, ensuring changes don't degrade existing efficiencies unintentionally. Future trends in algorithm design. Quantum computing promises revolutionary breakthroughs in solving previously intractable problems. Shor's algorithm demonstrates quantum advantage in factorization tasks. Machine learning models themselves optimize algorithm parameters automatically. Reinforcement learning agents discover optimal strategies through iterative experimentation. Edge computing distributes processing closer to data sources, reducing transmission latencies inherent in cloud-based architectures. Federated learning enables collaborative model training without centralized data aggregation, preserving privacy while maintaining analytical power. Conclusion: mastering algorithm efficiency equips developers to build robust, scalable systems capable of handling modern data challenges. By applying core principles and staying updated with emerging technologies, professionals can create impactful solutions. Implement these strategies systematically in your next project, profile regularly, choose appropriate algorithms, and continuously seek opportunities for optimization. Remember, small improvements compound significantly over time.